Hello everyone and welcome. In this video we will be discussing how to build distributed message queues. It is one of the important questions that is frequently asked in HLD interviews. Okay, so let's dive right into it. What is a message queue? A message queue is a messaging medium that facilitates asynchronous communication between components or microservices of a system. Okay? So what does asynchronous communication mean? Microservices do not have to basically wait for each other to communicate. They don't. It is not a request reply mechanism. No one waits for acknowledgement. Let's say there are two microservices. There is a producer and there is a consumer. Then the producer produces stuff and puts it onto the message queue. And whenever the consumer is free, it will come and it will consume the stuff from the message queue. So producer and consumer, they do not have to wait for each other. Okay. Now this is explanation of how a simple message queue is. Uh, why do we need distributed message queue? So let's say the number of producers and number of consumers in the system are in millions. So for that a single message queue won't be sufficient. That's why we'll need to build a distributed message queue, a message queue that is able to handle scale. Okay, so we'll build it. Let's dive into the functional requirements of this message queue. What do we need? So yeah, very first thing I would like to tell you is that this is a traditional message queue. It is not a message broker that is used in streaming services. It is a simple traditional message queue. So what a simple traditional message queue does, there are producers. The producers will produce the message and they'll put onto the message queue. So there are consumers, they will consume the message. Okay. Third is, a message can only be consumed once. So let's say producer produces the message and puts it onto the message queue. Okay, it has produced a message and puts it onto the message queue. Once a consumer consumes this message is consumed by a consumer, it should get deleted from the message queue. It should get deleted from the message queue. Okay, this is called as point to point model. A message put by a consumer can only be consumed by one consumer amongst all the consumers. This is called as point to point model. Fourth requirement is that the delivery order of messages, that is the way messages are consumed at consumers end, need not be same as the way messages were delivered into the queue. What I mean to say is the queue does not need to follow first in first out ordering. Okay? The queue does not need to follow this. We'll see why first in first out ordering cannot be followed in this distributed scenario. Okay? Now let's see what are the non-functional requirements of our system. The throughput should be very high. That is, the rate at which the messages are produced and consumed should be very high. And also we are talking about highly scalable system. That is, when there is demand surge, our system should be able to fulfill that demand. It should be able to add more nodes like that. There should be persistence. So once something has been put onto the queue, some message has been put onto the queue, even if the machine on which the message is present, it fails, the message should persist. Okay, the message should persist. The message should not get lost, even in case of failure. So that is what is meant by persistence here. Okay. Now we will be looking at the high level design of this system. Okay. The very first thing that we saw is message submission service. So what does message submission service do? The first thing that it does is it fetches from time to time, it fetches list of IPs for all the machines that are active in the message queue cluster. So whatever machines are active in the message queue cluster, it will fetch the IPs of all those machines from queue manager. Okay. Next, whenever a producer comes to the message submission service, it gives IP of one of the active machines to this producer. So here it is giving IP address of an active machine to the producer. Okay. Now, in what fashion does message submission service gives IP? So it makes sure that the message queue cluster will have a load distributed amongst them. Okay. So it should not be the case that the uh, one machine will have a lot of messages on it and other machines will not have, or very few messages in comparison to some other machines. So it needs to equally distribute load onto the message queue cluster machines. Okay. So what can it use? It can use round robin uh, scheduling. So it can distribute it messages one by one to all the machines. When all the machines are done, it will turn back to the first machine, and again it will give messages from first machine to the last machine. So one way could be that. Another way could be it will fix an IP for a particular producer. So whenever that producer comes, it will give that particular producer a fixed machine in the message queue cluster. So this is use case dependent, like what kind of load each producer brings in, and how do you want to distribute it. We'll usually want to distribute the load equally amongst all the machines in message queue cluster. So this is what a message submission service does. Next we see there is a message queue core, right? In message queue core we have distributed queues, we have already discussed. So it is cluster of machines on which queue is present, and the queue is partitioned over these machines. So the queue is divided into chunks, and it is small chunks of this queue are present on each machine. The third thing we saw is queue manager. What does this queue manager do? So this queue manager maintains the list of healthy queues, or the machines which are healthy on which queue is present. It will maintain the list of IPs for all these healthy machines. Now how does it do that? It will keep sending heartbeats to all the machines present in message queue cluster. So from time to time it sends heartbeats to machines, and if the machine responds to the heartbeat message, it means that the machine is active and it is working. So that is how it maintains the list of IPs for all the machines that are active in the message queue cluster. Next, the third thing that it does is whenever a machine goes down or a new machine is added to a message queue cluster, it will update the list of IP, right? So it keeps sending the list of IPs to the message submission service and message delivery service at regular intervals. Okay. Third, the fourth thing that it does is it transfers the jobs of unhealthy machine to a newer machines or active machines. Okay. So these are the things, these are the responsibilities that are managed by queue manager. These are the responsibilities of queue manager. Now the third service is message delivery service. So message delivery service is similar to message submission service. It maintains the list of all healthy machines on which queues are present, and whenever a consumer is added or deleted, its job is to redistribute the queues such that the load is evenly distributed amongst all the consumers. Okay? That is what a message delivery service does. So we have pretty much discussed high level design of our system. Now we'll deep dive into what database should we have and how do we ensure fault tolerance. So while talking about the functional requirements, we had discussed that we need not maintain the first in first out ordering of the message delivery. Let us discuss why that is not possible. Okay. So consider there are two producers, producer 1 and producer 2. Okay. Producer 1 produces message M1 producer 2 produces message M2. But if you look carefully, M1 goes on to a different partition and M2 goes on to a different partition, right? So on the consumer end, we cannot be sure that M1 would be consumed before M2. Why? Let's say the consumer that is going to consume M2 is free before the consumer, so let's name them as consumer 1 and consumer 2 only. So it may happen that consumer 2 may get free to consume M2 before consumer 1 is able to free itself for consuming M1. So the ordering of messages would change. While entering the queue, M1 went into the queue first and then M2 went. But while consuming, M2 may get consumed first. After that, M1 will get consumed. Because at the consumer end, we cannot ensure ordering. Any consumer can come and consume the message at any point of the time, right? So this is why we cannot maintain the first in first out ordering of messages at the delivery end. Okay. Now let's discuss what database should be used for storing the messages. So before deciding what database to use, let's understand the characteristics of the data that we are going to store. Okay, so the very first thing is that the data that we are going to store is both read and write heavy. What does that mean? At any given point of time, there are going to be lots of read requests and simultaneously there are also going to be lot of write requests. Okay, so a database is going to be read and write heavy. So the next thing is that the access is always going to be sequential. Why is that so? Let's understand now. So let's consider this is a queue. And this is the tail of the queue, this is the head of the queue. Okay. Now, whenever we have to put some data onto the queue or put some message onto the queue, it will always be from tail side. And whenever we need to consume something from the queue, it is always going to be from the head side. Okay. So if we maintain the tail pointer and if we maintain the head pointer of the queue, something that points to head and tail of the queue, then reading and writing onto the queue is both going to be sequential. Okay. When we are putting something onto the queue, we'll sequentially increment the tail pointer and we'll put the message. When we are reading from the queue, we'll sequentially move the head pointer and we'll be reading from the queue or consuming from the queue. So that is why the access is always going to be sequential. Next, there are going to be no in-place updates or deletes. So what do we mean by no in-place updates or deletes? Let's say there are multiple messages present on the queue. So it would never be a case that before reading M3 and M4, M2 needs to be read or M2 needs to be updated. So there are going to be no in-place updates. We are not going to pick a particular place and update there. This is what is meant by no in-place updates or deletes. The updates and deletes are always going to be sequential only. Okay, so can we consider SQL for this? If we consider SQL, how will we store? We'll have a table and each message can be stored in the form of a row. So a message would be a row. We can store in this way if we use SQL database. If we choose to use NoSQL database, then messages can be stored in the form of documents and these documents can be stored in a collection, right? So both SQL and NoSQL databases will be able to deal with this, but there is a problem. Both the databases can handle storage requirements very well, but it's very hard to design database that can handle both read heavy and write heavy systems at large scale. Moreover, databases are optimized for random access, but here we have sequential access. So we can exploit this property. We can use it to our advantage, that the data that is going to be stored is always going to be sequential. We'll see how. If not SQL and NoSQL database, then what do we use? We use something called as write ahead logs. Now let's first understand what write ahead logs are. So it is nothing but a file which keeps record of all the transactions. Okay. Now what does write ahead mean? Before any transaction is actually performed, we create a log and we append that log to a file. Okay, and that file is present on a disk, that is persistent storage. Let's try understanding this with the help of an example. Let's say we have a producer and it wants to enqueue a message MA onto the queue. So how will this happen? We'll first create a log. Okay, what does this log contain? It will contain these details. So it will contain what type of operation we are performing, then it will contain the message ID, it will contain the message payload, that is the actual content that is present in that message. The fourth thing that it will contain is the timestamp, when is this enqueue operation happening. And the very last thing is it will contain the offset. Offset means the position where the message is present in the logical queue. Okay. So once this log is created, this log is appended to the end of write ahead log file on the disk. Okay. So we created this log. Log contains all the details. Once this log is created, it will be appended to the end of WL log. Okay. Now once this log is written, only after that the actual operation is done. Then that is, this log is created. Now the actual enqueuing of the message will happen onto the queue. Okay. Now this was for the explanation purposes. The example was for explanation purposes. In our scenario, there is no actual op involved, since our WL or our write ahead log file is only going to maintain the queue. Let's see how it will do that. So we'll use the line number in the file as offset. And what did we see? What was offset? Offset was the location in the queue where our message is going to be present. So let's say this is our write ahead log file. It will contain logs. Logs will contain the message and position of this message in the logical queue. So our file, our write ahead log file, it itself acts as a queue. Okay. Okay. Now we see how will we deal with fault tolerance. So we know that the write ahead log file is stored on the disk, and disk is present on a machine. So this is our disk. This is our disk, and log is present on this disk in form of file. Now what happens if the disk itself gets corrupted? If the disk gets corrupted, all the files that are present on disk will get deleted. Our files represent queue, so all the contents of the queue would get deleted. Okay. That too, this will happen before the consumer consumes these messages. So we have lost our queue only. Complete queue, the data present in the queue is lost. Now how do we deal with this? In order to deal with this, we'll replicate our data. We'll use replication. Now how would this replication happen? So each partition will have replica. Each partition, what do I mean by partition? Each machine on which the queue is present, it will have a replica. Okay. And there could be multiple replicas, right? So amongst multiple replicas, there would be a leader. Each read and write request goes through the leader. So let's say this is our primary replica or leader, and whenever there is a read or write request, it will go through this leader. So let's say there is a producer and it wants to enqueue a message M. What will it do? The producer will reach out to the leader or primary replica. It will tell that I want to enqueue a message M. This primary replica would send this message to a synchronous replica. What is meant by synchronous replica? They will wait for each other's request and reply. Okay? So it sends a message to synchronous replica that we have got an enqueue operation. Once the synchronous replica has recorded this particular log into itself, it will send an acknowledgement to the leader that I have recorded this log and you can go ahead. Now once the leader replica once the leader has received the acknowledgement from synchronous replica, it will send the acknowledgement back to the producer that your message has been enqueued. Okay? Now if required, we can also have an asynchronous replica, right? What is meant by asynchronous replica? Synchronous replica and asynchronous replica need not wait for each other. Whenever they are free, they can exchange the messages onto amongst each other. So basically whatever log was put onto the synchronous replica, after some time that log would also be replicated over an asynchronous replica. Okay? They don't have to wait for each other's request and reply. So this is a bit counterintuitive. It need not wait for acknowledgement. Okay? So message is put on a synchronous replica also, and eventually it will also be put on an asynchronous replica. Now the number of synchronous and asynchronous replica can be configured based on use case. We can have two synchronous replicas and one asynchronous replica also, depending on our use case. Okay? Okay. Now we while discussing the high level design, we saw that there is a queue manager in our design, and there is a single queue manager here. What if this queue manager itself fails? If this queue manager fails, it will not be able to send the list of IPs to message submission service and message delivery service, right? If they don't have the list of active machines, producer will not be able to put messages onto the active machines, and similarly consumer will not be able to consume messages from active machines. So in this particular case, our queue manager becomes a single point of failure. So how do we deal with this? To deal with this, we'll also maintain multiple queue managers. One of them would be an active queue manager and others would be passive queue managers. Okay, and they will keep exchanging heartbeats amongst themselves. From time to time they will keep sending each other heartbeats, so that each one of them knows that this particular queue manager is active. Now let's suppose this active queue manager fails after some point of time. So when it fails, a leader election algorithm kicks in, and this leader election algorithm chooses one of the passive queue managers as the leader. Okay, and then from there onwards, the passive queue manager which has become leader will assume the responsibilities of a queue manager. Okay? Based on use case, you can select multiple leader selection algorithms. Some of them I have listed below. You can, if you want, you can check the details. So there is bully algorithm, there is ring algorithm, there is Paxos, and there is Raft also. You can choose any of the leader election algorithm based on use case. Now you may ask question that if the queue manager fails, where would the list of all the IPs of active machines go? If this fails, all the data would also go? No. For that, in order to deal with this, we'll maintain the list of active machines on a metadata store. This metadata store is independent of the uh, queue manager. It is stored separately, and this meta store is shared amongst all the queue managers. So even if a queue manager goes down, the data saved by this queue manager would remain intact. So failure of this queue manager will not affect the metadata, the data that we have stored about the active machines in message queue cluster. So this is how we'll deal with the single point of failure. I hope you would have understood this. Thank you so much.